Hello, we are here for one more lesson of this SprutCAM training course. And to remember, this is lesson 2 of the topic we've started in the previous video, which it is called the basic technology terms. So a couple more functionalities and the description of some things we can do inside SprutCAM. We will use the same model. I think it is good and enough to show you all the things we will talk about in this video. So let's start showing what we can do. First thing, it is something called the draft angle. And when we machine deep vertical walls, we may need to add some additional stock material every time the calculation and the tool reaches these vertical places. I will use this toolpath, this roughing waterline. We can see this in parameters as we have, besides these stocks, radial and axial stock, which we can deal and leave different values for each one of these stocks. Besides that, we can use also this relief angle, and in this relief angle we set an additional stock which we can use. So let us give you an example. And we can see the calculation with the relief angle of 0. So I will make the calculation with basically it is what was before. Going into simulation, simply checking the final result. So as you can see, especially in this area, we have this kind of material. Let's go back now. And for example, let's exaggerate a little and say relief angle of 45. Make again the calculation, and as you can see, we have already some different movements here. So simulation, and as you will be able to see in a couple of seconds, in these vertical areas, the behavior of the tool is different and it will leave an additional stock. Then we have other things. Let's go back. We have other parameters. One very important, it is something called machining step. And this machining step can have different formats, because it can be different from toolpath that, like this waterline, creates these vertical layers, or a finishing toolpath which moves on a different way. So even on this waterline toolpath, we can try to simulate it. As reset this and do a little slow. So if you see, from one pass to the other there is a distance, and this is a step. So we can define these steps. Let's go again. We can define these steps in several ways. So we can do this by distance or percentage of the tool. So if I say instead of percentage of the tool, which is 75% now, I can say distance, and I can say, for example, let's exaggerate a little, so 10, and we will have a completely different toolpath. I will change these parameters again to the 0, sorry. It will give a clear result. So let us try to simulate it. We will reset the model again, do another simulation, and as you can see, it creates these big steps that in the end, because it's 125% of the tool diameter, leave this excess of materials, which is not desirable, but as an example, it is nice to understand what we have. We have this kind of step. So strategy, we have this kind of step, so we can leave this percentage of the tool, we can have this as a distance. And we have another kind of step, which it is used for finishing operation. So we have this kind of toolpath, which is a finishing plan. And if we open the strategy, we have also something called step, which has also distance and percentage of the tool. But we can have this as a different thing, which is a scallop height. Okay. But first, the step in this particular toolpath is much smaller. So we have one, but we can lower this, for example, for half a millimeter, and we have a more dense toolpath. So it is what defines the density of the passes. In terms of this step, we can connect this, for example, with this parameter, scallop, and the scallop, instead of having a fixed distance, we can define a value which is the amount of material, this scallop here, that it is the maximum the program accepts. So if I reduce a little this parameter, for example 0.05, so we will have different distances. As you can see, we have different distances. In some areas a little more dense, and in other areas a little more far away from passes. And this kind of parameter in the finishing toolpath will create a very stable and a very uniform amount of material in all the parts. So it is also very interesting and very useful in terms of toolpaths. We can use this not only in this type of toolpaths, but we can use these kind of things, for example, when we are doing finishing, for example, finishing by a water line, because we may have also angle walls which are interesting to have done by this strategy. I will not do this toolpath, but the principle it is the same. We have also something important, which are the milling type. The milling type can be seen here, and it's the cut direction, which can be climb or against the material. You see the graphics, the rotation way of the tool and how it moves, or conventional, which is the opposite, or if it is not important, it can move both ways. It depends on the tool, and it is something that in some types of tools it is important, in other types it is not important. It depends. It's a basic parameter also. Then we have, especially in some types of toolpaths, for example, in this finishing toolpaths, we have something called the step-over method. And the step-over method can be seen in this transition area. So step-over type, the graphic, it's also very clear. So it can be done on surface. It can make a retract approach movement, or it can go up via the safe plan, and then we have some distances. We can try to calculate this so that you can see what is the difference. So every time it comes out for changing direction, it goes up and makes the change on the safe plan. So it's I will not say that is good or it is bad. It is a strategy which in some situations may be interesting. I would say most of the times it is not interesting, because we should have the part prepared so that this step over, to avoid losing much time, can be done on the part, but it's a way. There is one other parameter also called roll type, and roll type it's used if we have, for example, a curve. If we have a curve to define the area, or if we consider to mill a part, a complete part. So let us see a couple of examples, as we have three options. So surfaces only with edges, or the restricting model. So surfaces only, we can calculate this, and I will take this out to be a little more clear. So transition on surface, and now let us run it again. So as you can see, we especially in these areas, and I have also the step which I will take out, so using 1 mil to give a clear path. So you see that in some areas, and this vertical one, it is very clear, the tool does not move until the bottom of the surface. But if I change this, for example, to not this one, to with edges, it will have a different behavior. Okay, a little more down, and if I choose the model, then it should come all the way down. Okay, different strategies to limit the area where we can work with the tool. Another important parameter, which is the pass angle. So the pass angle, it is something we have also in a lot of milling toolpaths. This angle 90 degrees, if we see, it's always on the same direction, but we can do, for example, and it is common to use, for example, 45. It depends on the shape, so you see that completely different, and it will move two axes at the same time. So this is something possible to define in a lot of different toolpaths. Another very interesting parameter also, it is the maximum slope angle. It is something that we have, this slope angle allow us to work on a range of angles, and every time a calculation it is done, will the program will work only on a specific part of the surface. For example, now we have 1 to 90 degrees, and you can see that basically the part is completely milled. But if I change this from 1 to 45, then I will work only on flat surfaces until 45 degrees. So if I run here, you'll see that basically I'm going only on this flat area. I have these parts here because I have the where it is, the trimming surfaces only, so I will not go down with the tool, and now I have something much more clear only on the easier parts of the surfaces. So I can have this limit done by angles, and I'm free to, instead of having one, I could say 45 to 60, and I have a very small range, but I can use this kind of approach also. So I have this kind of appearance also in my toolpath. Another interesting characteristic, I will say again 1 to 90 to have a better viewed toolpath. I have something called the upwards only. So instead of going up and going down, the strategy will be, for example, in this kind of shape, I will mill in one side upwards, and I will go on the other side and I'll do the upwards also. So it will give this kind of look, because every time the tool reaches up, needs to go save plan and change to another place. So it's a little different approach also to work. Going back to this roughing waterline, 2 or 3 more different things. First one, something called the machining order. This graphic, it is quite interesting, because not this model, maybe it's not the best suited for this parameter in particular, but every time we have something with a lot of pockets, this type of tool by levels, every time it cleans a level, and if it finds an area, a closed area, where it needs to go up to go to another place, we can choose this by layers, or it will clean completely a layer and it will go up the times that he needs, or doing by cavity. So when he finds that it is closed in one specific area, it will go down until cleans all that pocket, and then it will move up again where it was to clean another area. So it is a very interesting idea also. We have a program here which I will calculate. It is something called morph. This morph will grab a curve or a specific area, and it will create something like this, which it's something, it will respect the area. So instead of having these fixed contours, it will evolve from the contour. It depends of what it has. But the interesting part of this, it is the possibility. Let us try to open this toolpath. Oh, I got a mistake, but let us try to open it again. It seems that I did not like. Okay, I don't want. Sorry for this minor issue, but okay, it happens sometimes when we are playing with the parameters, and if we don't take care of things. So in strategy, we have something called, and we have more types, but to have this specific example, so we can do the across, and the across, let's try to run it, will grab the same area, so, and it will make something like this. If I go there again and, for example, change to the along, will be completely different. So this type of behavior, and we can try the other one, which seems that it will give us problems again. does not like very much of playing. Okay, sorry again, but does not like this. So open the model again once more and going there again and doing this spiral thing and run it, which it is a little different from the other one, but so that you can see the difference. Finally, we have, and going back again to the roughing waterline, we have this machining strategy, and we enter this trochoidal machining, and we have on this type of toolpath, we have this machining strategy, which can be equidistant, and then we have parameters to give in terms of behavior, so we can have corner radius and so on. But we can have this equidistance, we can have the parallel behavior, or we can have this type of adaptive mill or high performance cutting, which is the trochoidal or deep cutting. A lot of different behaviors, and the adaptive, which is similar to this one. So to give you a couple of examples, let's try to calculate 2 or 3 of those. So equidistance, it is the easiest one. We can have this finishing radius. I will leave this 0 now and do the run. And we have a very simple toolpath. As you can see, for example, we have these sharp corner places where it changes direction. But we can insert, for example, a 2 mil radius, and it will have a completely different thing, or at least I hope in some places, which I did not see in, oh sorry, not the finishing, it is the rough radius, my apologies. Okay, then you see now I have this small radius, okay, which will give a completely different behavior in terms of the toolpath. This is one of those. We can have the parallel one, okay. Let us try to calculate something. I did not see the direction, okay, but as you can see, okay, a lot of going ups, which is not good in terms of time and behavior, but so that you can check what this does. The adaptative, which it is percentage of the tool. Okay, I think it will not take too much time. Okay, no problem. Let us go and calculate the tool path. And you see, which is, it is a very dense, does not have, let's see, you cannot see any sharp corner, so it's very smooth for the machine, but you need to have a very fast machine because it will cut a little portion of material each time, but always moving. So very interesting, but you need to have a good machine to have this. We can have this type of trochoidal. Let us calculate, hopefully not taking too much time also. This, you see that it has some movements around here to change directions and so on. This is very interesting type of toolpath, very efficient. And to end this deep HPC, I will increase a little this distance. Okay, this is also very interesting toolpath. A little more dense, but very nice in terms of the movements, which we can try now to make a simulation. Let us hope a little slower. Let us try to see something. speed up this. As you can see, the movement is very smooth. Okay, takes small portions. I've increased a little. I put 50%, so we should have a small. We had 10, but it was to make the toolpath a little with a little more speed. But I think it gives you an idea, a very nice idea of what is possible to do with all these different parameters. So I hope all of these topics were clear enough, and I would bet that for sure with this you'll have a couple more tools to try in your work. If you need more explanations, let us know. We are here to help and to answer to your questions, besides our online platform, which has more information. As you know, also we keep repeating this. So contact us in case of need about this or other topics of SprutCAM.